Hello everyone. Today I'm gonna apply neural network to predict the performance of our devices. So let's import the libraries. For neural network, we have to import some additional libraries such as TensorFlow and some pre-processing libraries such as standard scalar. So let's run code cell. So in this code, I have migrated my dataset into the Google Drive. If you press Mount Drive, and this code will be inserted, and you will be able to um, use your dataset from your drive instead of dragging it each and every time. So the mount is complete, and this is the location where I have placed my dataset in my Google Drive. Everything else is the same. So let's run this cell and handling missing data. Encoding categorical data, it's all the same as before. And just to test our output, splitting. Now for neural network, we have to do something called feature scaling, and let me explain the concept real quick. So now we have our model, um, and the input features with different units. So the observers are from 0 to 3, and the thickness are from 0.1 to 1 micrometers, and defects are from this value to that value, and same for the donor density. But in order to apply neural network in our code, we have to do feature scaling, which will then take all the different scales for these four independent variable vectors into one scale. And in my case, the values varied from +2 to -2. So all these features will have the same scale now. So feature scaling is a pre-processing step that transforms our data to make it more suitable for deep learning models. We apply feature scaling to improve the convergence speed, and this also helps to improve the model accuracy. So now let's implement this into our code. So we have imported the scalar object as the standard scalar, and we have to fit our xtrain and xtest according to that. So let's run this cell. Now if you see here, all those four different scales have become one scales with roughly values roughly around +2 to -2. We can actually check this range. So if we type the highest value as np.max from xtrain, and the lowest value as np.min from xtrain, we can see that the highest value is around 2 and the lowest value is around 1.5. So now let's build the neural network. So the neural network is a broad topic. I will not go into the details, but in our case, this is what a neural network looks like. So in our case, we have inserted two hidden layers between the input layer and the output layer. So our input layer had four features: the observer names, thickness, defect, and donor. and we have inserted 64 neurons for hidden layer 1 and 64 neurons for hidden layer 2, which is a basic standard um, number for neural networks. And the output layer, we have just one neuron, which is the PCE. So let's now go back to our code. This is the input layer and the first hidden layer. So dense means all the layers uh, are fully connected. So each neuron is connected to every other neuron of the neighboring layers. So units equals 64 means we have taken 64 neurons for the first hidden layer and 64 neurons for the second hidden layer, and the activation function ReLU or rectified linear unit has been applied. This is a standard activation unit, and the input dimension is set to xtrain.shape, and this specifies the number of features in the xtrain. So we have 4 features in our xtrain, so input dimensions will be 4. And for our output layer, we have set the units equals to 1. Since this is a regression task, there is only one neuron in the output layer to output a single continuous value, which is the performance of the devices. And for the activation function, we have set it to linear. And so for regression, a linear activation is used. So for neural network, we have to set a parameter called the loss function, and we set it to mean square error, and another parameter called the matrices, and we have set it to mean absolute error. So mean absolute error provides an intuitive measure of the average error magnitude and is helpful for interpreting the model performance. So this code will train the neural network. The batch size equals 32 means that the number of samples the network will process before updating something called the weights. And the epoch is set to 100, which means that one epoch is a complete pass-through of the training data. So let's run this cell now. This might take some time. So the training is complete. Now we have to evaluate some things. So the test loss and the test MAE, or mean absolute error, um, will be the evaluation factors for our neural network model. So since our model is a regression problem, so the lower MAC, or mean squared error, indicates that a better performance, and the mean absolute error, or MAE, will give the average magnitude of each errors between the predictions and the actual values. So let's evaluate our model. So this is the test loss and this is the test mean absolute error. Um, so we can also plot the validation or the training history to further evaluate our model. So if we run this cell, we will see a plot something like this. Now the history loss stores the training loss for each epoch, and the history validation loss stores the validation loss for each epoch. Basically, if both the training and validation loss decrease and then flatten after a certain epoch, this suggests that the model has likely reached a stable point and is no longer improving significantly. So this trend means our model is good enough. So let's predict the test set results. Most of the values are close. Let's evaluate the R2 score. So our R2 score is 996. Now let's do the scatter plot. For neural network, I have just added this line of code, otherwise it doesn't work. So I have reshaped the y prediction uh, to be able to plot this curve. The y pred, it changes slightly in the neural network, so I have to reshape the y pred before continuing. So this is our scatter plot, and the shape curve for the neural network is significantly different from the other regression models, and also this will take a lot of time to execute. So after maybe 15 minutes, the shape plot is finally ready. It's all the way down here. So thank you guys. That's it for this video. The codes and datasets can be found in the description.